We're going to talk about system applications and piping. You will see another webinar coming up called installation in piping, so it'd be a little bit different than this one. This one, we're going to talk about all the components in the system and how they would all go together as pieces and parts. We're not going to spend a lot of time on pipe sizing and stuff like that. That'll be handled in the other webinar I just mentioned. So just to get going here. Okay. So our objectives today are to identify various heating, cooling, and DHW applications, describe several possibilities for piping configurations, and indicate the control wiring that supports this piping application. Again, we're not going to do wiring. We've already done that. So we're basically just going to point and shoot. We're going to say this part connects to this part. If you want to know what terminals are hooked up to, that's the webinar we did a little while ago on wiring. And together they will be help you with that whole package. So, just a quick review of things we've done before. There's basically two systems that we're going to look at here. One is, you have an outdoor unit, you have the indoor unit, you have an optional indirect tank with the buffer tank sitting on top of it. And in this case, we're showing a forced air, hot water, chilled water air handler. And then again, we also have the option of adding a backup boiler or an auxiliary boiler. So we'll talk about all of those things as we go through here today. Anything I'm going to talk about today, and just to be clear, this is not a Bible of what you should do. This is suggestions and things we've come across with talking to contractors and our own interconnections between the Academy boys, and we've said, this is an application and this is an application. Certainly, there's going to be stuff that you maybe want to do in the field that is going to be different or an augmentation to this or less than this, depending on what we're going to talk about. But we're going to give you some ideas and some suggestions. And anything we talk about today is suitable for all three of the sizes. So the first thing we're going to look at is the outdoor unit and the connections. So all the connections in the outdoor unit are all 1 inch, and you can see the H and the I referring to the drawing here. The native connections on the unit are 1 inch, but so is the air scoop and the pressure relief valve. That whole area ends up with a 1 inch termination. Now, that's not to say you're going to use 1 inch pipe for every application. This is just an indication of where we're starting with. And again, they'll go through the details of pipe sizing in a future webinar so that you can get pressure drop and friction loss and those kind of things. And the indoor unit will be very similar. We're going to have inch and a quarter on the actual unit, but by the time we go through the adapters and valves, these isolation bypass valves that you see, these Webstone valves, everything's going to be 1 inch at the end of this. So it's important that you understand that we start out with 1 inch, and you may or may not be putting bigger pipe depending on how far you're going and what size of unit you're doing with. And again, they'll be covering that in future presentations. Buffer tank is standard with this, so it's a 75 liter or 19.8 gallon buffer tank, and it was designed for this heat pump system. So I know there's been other people saying, well, what can I use a buffer tank that I prefer or whatever? Yeah, certainly you could substitute a different buffer tank as long as it had the specifications of the press separation that you need in a buffer tank. But this is what comes with the unit. You're already buying this because it's come stock with the unit. So in most cases, you're going to use the buffer tank we supply. Now, as far as the connections on that, again, are 1 inch. Everything is 1 inch all the way through the board here. There's two temperature sensor wells, and we're going to show you how we're going to look at one of those sensor wells for a possible application. Then we have the optional indirect tanks. So these are glass line tanks that were specifically designed for these heat pumps. They have a much larger coil than our standard stainless steel tank, and they have this special electronic anode designed for these tanks. So these are the tanks that are matched with that unit. Now, you may be able to use a different tank, but I'm going to talk about a few options here in a second here. If you're using the indirect tanks that come with the heat pump or designed for the heat pumps, the glass line tanks, the buffer tank is designed to mount right on top of that. So if you have enough headroom in your boiler room or in your mechanical room, you can put it right on top. If you don't, you can put them side by side. And if you were going to use, let's say, our stainless steel 2-coil tanks, because that would be the only version we would have that would have the right surface area for heat exchange to be equivalent to the heat pump tanks. And they are doing some retesting on those. I don't know if they've got them all published in the manuals yet for lower temperatures, because we typically have not tested our stainless tanks for the lower temperatures because we've been using them for boilers, right? So boiler water temperatures. So if you are going to use another indirect tank, either a stainless steel tank from us or somebody else's tank, you would need to put the buffer tank on the floor on a rack or something. You wouldn't be able to put it on top. It's only designed to be on top of the tanks that we supplied with the as matched with the heat pumps. And then again, there's always the possibility that you're not going to do DHW, so your buffer tank would be on its own, like it's shown here. So just a quick run through of the things that are happening. What we're going to talk about today is the connections between indoor and outdoor unit. And you can see that the indoor and outdoor unit are connected here through these two pipes here. And then once it's inside the indoor unit is responsible for adding the electric heat when it's necessary and sending it to DHW or to the buffer tank, and then everything comes back to here. So just as an internal function, the indoor unit is managing flow to the system, so either to the buffer tank or to the indirect tank, and it will also manage the set points and things like that. All your control logic for operating this heat pump is going to be in the indoor unit. Now, let's take this in little pieces here. So we're going to look at the part of the machine that is responsible for the energy. So, when we have a heat pump that's outside, and heat pump doesn't create energy like a boiler necessarily does. You put a gas boiler in there and you have a burner and you fire the burner, and you're going to have efficiencies that are going to turn into heat. So when you burn the fuel, you're going to take the heat. So you're actually taking the stored energy in the gas and creating heat out of it. With a heat pump, what we're doing is we're moving heat. We're taking the heat from outside of air and putting it into the water, or we're taking heat from the water and rejecting it to the outside air in a cooling application. So this is a machine that's going to move heat in or out depending on its application. And then we have the indoor unit, which is going to be responsible for taking that energy, whether it's moving it in or out, and distributing it either to DHW or to the buffer tank. And we'll have the ability to add electric heat here under certain applications of outdoor temperature, and we'll talk about what we call those values later. We've used the term bivalent point, but the bivalent point and word bivalent point actually isn't in the control, so it's a concept point, and we'll talk about how we use it in the few slides forward. So you have, this is basically where the energy comes from. It's either moving it from the outdoor air, putting it to the outdoor air, or we're adding the electric heat, and this is what this portion of the machine is from. So this part of it is we could call it the heat or the cool generation. Now we're going to attach that, like I said, with the electric heat, and we can do up to 9 kilowatts of electric heat, and in smaller one, the 2 units are 6 kilowatts. Now where does that go from there? Well, it goes to the distribution system, which is the buffer tank. So when it's in a heating application or a cooling application, the diverter valve sends water to the buffer tank through these two connections here. And then this becomes your stored energy. So either chilled water or hot water, depending on how you're going to configure the system and what your control is set for in that particular day. It's either going to be chilled water or hot water. And the idea is this is a value or a reservoir of energy that's there. So the heat pump doesn't have to deal with those small load changes that you might see in a radiator or in an air handler or whatever that's going to turn on and off in the system. And then from the system point here, these two pipe connections connect to the system, and we'll show you some examples of those later. Now, there are a couple of different ways we can look at temperature in this buffer tank. The first one is the buffer tank comes, or the unit comes with a strap-on sensor for the energy circuit water, heat cool circuit 1, HC1. And that would be by native, if you wanted to strap it to the pipe, you could strap it to the pipe here, which is the return piping to the indoor unit, and it needs to be as close as possible to the tank. Now, the downside of this is when it's making domestic hot water, there's no flow in this pipe. So if you're drawing chilled water or hot water off of this tank is going to be starting to either cool off or warm up, depending on what you're doing. And this sensor is not going to see that in this position. So you have a couple of other options you could do here. You could use an immersion sensor, which is a sensor you could buy as an option, immersion sensor. But our lab tech has done some testing on the strap-on sensor, and by nipping off the strap and putting it into the immersion well, then this could become an immersion sensor using the sensor that comes with the heat pump. And if you'd rather have a more designed for an immersion sensor, there is the option of buying another immersion sensor, and you can use it. So this is totally your choice. I know there's guys who are more familiar with the controls than other guys, and they might have a methodology that say, this sensor does this with 360 degrees pickup with the strap-on sensors. And we've done testing on it, and it doesn't seem to be a lot of difference, if any, between the two, but it's totally up to you how you want to do it. But you can nip off the strap on the strap-on sensor, or you can buy the optional immersion sensor, and then it just fits right inside the well of this tank. Now, the upside of this is that when there's no flow here in this piping to the indoor unit, and you have flow here for the system, while the system is making, let's say, domestic hot water, this sensor will know the temperature of this tank. It will know it's deviating from the set point. So when it switches back from domestic hot water, it will already know how far away from the set point it is, as opposed to when over on this side where we had to wait for the flow, and then it would see that temperature drop or rise, or however we're going to look at it for cooling or heating. So this is, in my opinion, this is a more accurate way to do it. This is putting the sensor in the tank, allows the control to see what's going on in the tank in real time all the time, and it will make it a little bit more accurate, in my opinion. So there are a couple of other options we could do here. What if your building doesn't want, or isn't suitable for, or the customer doesn't want it, glycol throughout his whole building? In the native of this, we're going to put glycol in the system in northern climates, obviously, and we're going to send that to the buffer tank, and then it's going to send it out to the heat emitters or air handlers, or however we're going to do that, and the whole system is now full of glycol. There may be some instances where that's not suitable, and it may be a preference of the engineer, it may be a preference of the homeowner, it may be the type of piping you're using, it may be the pumps that are in the system, because remember, if we put glycol in it, we're going to have a different pressure drop and friction loss, because glycol is more viscous, right? So what you're going to need to deal with, maybe your building doesn't have pumps that are suitable for glycol when you're replacing the boiler or something like that. So this is the option you can do. You could put a heat exchanger in here, which is a glycol to water, and I'm showing a flat plate heat exchanger here, but any kind. This is probably the most common version you're going to see, but a bundled heat exchanger, a tube and tube, or tube and shell, or something like that would work as well. But this is a flat plate, which means that on this side we have water, and on this side we have glycol. Now, there are a couple of things we want to look at for this. So we talk about adding this heat exchanger, which means that we also have to add a pump, because now we basically have a separated flow system. So this pump here, being a glycol, we'll call it a glycol pump sized correctly to move glycol from the outdoor unit to the heat exchanger. We're going to be controlling that from the indoor unit. On the indoor unit is an output called glycol pump, and we wire it to here. And then anytime the indoor unit has a call for energy, either to or from the heat pump, its pump is going to run, and we're going to circulate water run this way. Now, in a lot of cases, we're going to put a bypass in here. So if we're going to put a bypass in here, we want the bypass on the glycol side of the heat exchanger, not on the water side of the heat exchanger. And here's the reason why we want to do that. If we had this bypass on this side, and we were using the indoor pump, and we were supplying water and bypassing and going back to here, and this pump here was still moving water or glycol water to the heat exchanger, we could get into a position where this side would be below zero glycol water. That's fine, it's not going to freeze, but the water that's in this plate is just going to be boiler water, just going to be treated system water, and we don't want this to freeze. So to solve that problem, we put the bypass on the glycol side, so that way the bypass is here, and we always have the boiler water or the system water, whatever, traveling through this side. Okay, so that's an important thing to remember if you're going to be putting a heat exchanger in and you want a bypass for servicing and that kind of thing, that you put the bypass on the glycol side. Now, what if your piping is long distance? You got a long distance between the outdoor unit and the indoor unit. Well, if that happens, then that poor little pump in the indoor unit that's designed to move water from the outdoor unit to the buffer tank and back may not be strong enough. It may not have the head friction loss capability at the flow rates we need. So what we want to do here is we want to do something a little different. So looking at this, we see this is very similar to what we did with the heat exchanger, except instead of a heat exchanger, we're going to use a low loss header or closely spaced tees or some other form of primary, secondary, right? A buffer tank or something like that. And again, we're going to put the bypass on this side just because we can eliminate any issues with this. But this system is all glycol, right? So remember, this different than the heat exchanger where we had glycol on one side and just treated water on the other side. In this system, the entire system is full of glycol. So again, to control this pump, we're still going to use the pump output. I see my arrows have moved. The pump output to the pump from the glycol output. So it's still called glycol pump in the unit, still does the same function, except we're going to be all glycol in this as opposed to separating it with the heat exchanger. The entire system is glycol in this application, and it was boiler water on one side of the plate exchanger. In some instances, we may not have enough energy all the time. An air source heat pump of any kind, air to air, air to water, as the outdoor air temperature changes, the heat pump is going to have capacity changes. As it gets colder outside, we're going to have less ability to pull heat out of the outside air. And even on the other side, on the positive side of this, the hot side of this, once we get up to a certain ambient outdoor temperature, it's hard to reject the heat because the ambient around it is hot. So we have to look at this scenario from a heating perspective. We can say we may need a backup boiler. So you see the backup boiler, how we've piped it here. We've piped it in closely spaced tees in line with the line that comes from the outdoor unit. So this is how we would be able to supplement the heat. Now, this boiler could be any boiler. It could be a brand new boiler you bought for this. It could be the boiler that's existing in the boiler room and it's already there. You're just going to repurpose it, repipe it so that it's used as the backup. And there is a dry contact in the indoor unit to enable this boiler. And there's an adjustable set point in the indoor unit called auxiliary heat enable temp, which will be the point at which we're going to say, in this installation, wherever I am in North America, in Fort McMurray, Alberta, or Minnesota, or Texas, you're going to have a point where you may need the heat augmentation because the heat pump can't move energy at that certain outdoor temperature. So when this is enabled here, when this point is enabled, then once that is enabled, the indoor unit sends a signal to the boiler, says, hey, you're in charge now. You're doing the heat. We're not giving it a set point. The set point is coming from the boiler itself. So you're going to have to set the set point in this boiler for the design temperature you need. And remember, it's probably also doing domestic hot water. So you're going to have that boiler water hot enough to do the hottest load, either building heat or domestic hot water. And that's a number that you're going to set. And you're probably not going to use a heating curve in this boiler because it's only being enabled when it's cold outside. So you're probably just going to run a fixed set point, but you have to determine that set point is based on what you're going to supply heat to. Now, also, when this boiler is enabled, when this indoor unit says, hey, boiler, you're in charge, we disable the outdoor unit's ability to move energy, and we turn off the electric heat. So this boiler has to be sized for 100% of your building load. It's not saying, well, the heat pump plus this boiler, the electric heat plus this boiler. This boiler is 100% in charge of the heating of the building when it's switched to that system. So make sure that the boiler you're using is big enough for 100% of the load, whether it's heating or domestic or whatever the larger of the two are. That's what's going to need to happen, okay? So if you don't have any domestic hot water, you could put this boiler directly connected to the buffer tank. There are two tappings for second heat generator on the buffer tank, and this works perfectly fine to load the buffer tank up and maintain the heat, maybe even a little bit more accurate because we have a much less, shorter run of pipe here, and this is going to be maintained at whatever the boiler set point is. But it doesn't work if you have the DHW because the tank is here. When it switches to DHW, which I don't show in this drawing, but when it switches to DHW, there's no way for this heat to get to the buffer or to the indirect tank. So that's why we've shown it in the other position in the previous drawings. Okay. Now, looking at this drawing here, again, we put the boiler here. In some cases, you might want to put this automatic bypass valve on it. And the reason why we say it's optional, you don't have to do this. Okay. But think about if I'm generating heat from this boiler and I'm going to be sending it to the system, some of it's going back to the outdoor unit and back to here. So my outdoor unit is going to be eating up heat just by ambient temperatures, right? Just by the heat loss through the ambient temperature. The heat pump's not providing anything for us at this point. So we might want to put this electric bypass valve in here, and it would be a powered open spring return type valve because we're only going to power it one direction. We want to power it. Basically, we're going to power it closed, and when it's not being closed, we're going to power it. We're going to let the spring return it open. And what I mean by closed is closing the path through here. We're going to bypass it so the water goes around like this, right? And it essentially then blocks the flow of water to the outdoor unit and allows it to recirculate on a shorter circuit here so that this boiler energy, where the gas we're burning and the electricity we're using to generate heat, isn't being lost to the outdoor unit. Again, this is an optional unit. There are maybe some installations where the contractor or the engineer might say, hey, we want to always circulate water out here for whatever reason. And that's fine if that's what the design is for, but you'll have to take into account then your boiler has to be sized for whatever the energy loss is going to be out here, right? Now, it is again controlled by the boiler. So something in the boiler's output, usually it's a pump output, will close this valve so that the water can't go through this way and it bypasses this way, right? So just remember that the boiler's controlling this valve. And these boilers are going to be just an on-off signal, so that's why we're powered open spring return. And piping it correctly as well, right? Because we want to make sure that the bypass is blocked this way and open this way when the power is on the valve. Now, when we look at the DHW on its own, and there may be a possibility that this system is just DHW, right? Maybe this is what they've designed to do, and that's possible. I don't think we're going to see a lot of that, but it is possible. The outdoor unit, the indoor unit moves the energy from the outdoor unit as it heats the water up, because essentially it's in a heating mode, even in the summer. It's going to come through here, and it's going to come down to this line here to the indirect coil, and it's going to be based on the sensor that's in the tank. The sensor in the tank is connected to the indoor unit, and it's going to have a set point in the indoor unit for your domestic hot water. And when it drops below the set point, we're going to start up the outdoor unit. And in some cases here, we might be able to augment it with the electric heat at a set point we call IDU element heating enable. And that is in the control under the heat pump group. Above that set point, whatever point we pick here, then the electric heat isn't involved. The outdoor unit is 100% responsible for it. Below this set point, we can also add the electric heat after the time delay that's built in the unit. And DHW in this system is always priority. Your DHW will always be priority in every application. And of course, the indoor unit then also has the ability to run the domestic hot water recirculation pump if that's installed in the system, and you can put a schedule on it if you want to do that. It's part of the control logic. So once put it together, and again, we'll go back and look at without DHW, we looked that up to the buffer tank, but let's look beyond the buffer tank. In this application, we see an air handler. Now this is maybe heating only, maybe it's chilled water only, maybe it's a hot water, chilled water air handler. It doesn't matter. And you're going to set the function of hot water or chilled water based on how you have the control set or the jumpers that are in there, right? But the heat pump is going to move energy through the indoor unit to the buffer tank, and then the air handler is going to draw off the buffer tank. But because this air handler has its own pump output, we're not going to use the pump output for the heat circuit or cooling circuit 1. It's going to be active inside the unit, but we don't have anything connected to it. We're going to use the air handler's pump, which will be triggered on by the thermostat calling for cooling or heating, and then our buffer tank is going to pull the energy. Now, there is a possibility that somebody turned the thermostat to cooling and the heat pump is still in heating, which means that this pump is going to move hot water, not cold water, because the buffer tank's going to be full of hot water. So this is a seasonal changeover. You would not normally set this thermostat to automatic changeover. You would set the thermostat to be heating or cooling and switch it at the same time you switch this unit down in the indoor unit. Now, it could provide heating or chilled water depending on the control system settings. Remember, so we have this here, and the air handler would have to be suitable for that type of energy. And the reason why I point that out is because we have had some contractors try to use air handlers that are heating only. So they have a flat horizontal coil. They don't have control logic for chilled water. And they're saying, well, the pump won't start for chilled water. Well, no, it's not designed to start for chilled water because those air handlers that are heating only are designed to have DX cooling in the ductwork. So the cooling logic is just a Y1 and Y2 command to turn on a DX system. So you make sure your air handler is suitable for hot water and chilled water, or the option would be to put a chilled water box coil in the top with its own control logic and potentially its own circulator. So it's much simpler if you just pick the right air handler off the boot. Viessmann currently is in development of an air handler like that. The air handlers we are selling in North America are hot water only. So this would be something that would be coming in the future from us. But just to be aware of that, the air handler, if you're going to use this for hot water, chilled water, the air handler has to be suitable for that. Now, again, we take that same application. We had DHW. So we have a heating, cooling circuit 1, and we have DHW. So the indoor unit will switch this unit from domestic hot water to heating and back, but it can also then, like I said earlier, control the recirc pump. And the tank sensor in the tank will be what is feeding back to the indoor unit to say, we're going to switch to DHW. Remember, DHW is always priority. So this looks at a different kind of a heating application. So rather than the air handler we looked at, this is a series of panel rads. And in most cases, these panel rads are going to be heating only. I mean, there are panel rads and heat emitter rads or cooling emitter rads. They're designed for chilled water. And if that's the case, you could do heating or cooling. But I think in North America, I'm not really aware of too many applications where we're doing anything but heat with panel rads like these. And I'm showing you in this drawing thermostatic valves on the rads. And that's fine. That works. And that's a very common way to do it. But in a lot of cases, you might have motorized zone valves with thermostats. And it doesn't matter which way you do that, because we're not going to take anything from here, any brain from here that says I need heat, and feed it back to the indoor unit. We're going to let the indoor unit keep the buffer tank hot, and the building is separated from that. The only connection we have in this case is we have the heating, cooling circulator pump is going to be running on circuit 1. So where the air handler had its internal pump, we didn't use that circuit. In this one here, we are using that circuit. So now we get in a little bit more detail here, a little bit more sophistication or more equipment. And in this case here, we have circuit 1 and we have circuit 2, which is a mixed circuit. So remember, the indoor unit is going to control both pumps, and it's going to be different set points, maybe different heating curves. Maybe this one is hot water, chilled water because it's radiant cooling, or maybe this is hot water, chilled water because it's got radiators designed for cooling. In either case, that's a function of the control logic, how we set the system up, which will determine when or how these pumps run. But there are two circuits. So we have two different set points, right? Two set point for the panel rads, set point for, in this case, the mixed circuit. And the indoor unit will also control 120 volt output, powered open, powered closed, to the mixing valve. Now, this is by factory designed for the Viessmann 120 volt mixing valve. So the timing is correct for the R valve. If you're going to use somebody else's mixing valve, then you would have to go into the control setup and set the stroke time for your valve to match whatever the in the indoor unit control logic would have to match the timing of your valve. Again, the simplest way to do that, use a Viessmann valve, and there's no adjustment you have to make to the timing because we've designed this for the Viessmann valve out of the box. And then the temperature sensor for circuit 2. Remember, the temperature sensor for circuit 1 is in the buffer tank. Temperature sensor for circuit 2 is in the pipe downstream of the mixing valve, so the mixing valve can control it. In the heating mode, this mixing valve will modulate to maintain the hot water temperature based on your outdoor reset curve. And in a cooling mode, this valve just stays wide open. And this is going to be basically part of the logic that says, what temperature do we run this heat pump to for chilled water? Chilled water does not have a heating curve. It's a fixed set point. The default is 45, excuse me, 45 Fahrenheit, and it's going to be 45 Fahrenheit. That's a pretty decent number for chilled water because it gets it down below the dew point, so you get sensible heat and latent heat removal. If this was radiant cooling, we would have to add some extra controls or make sure that the set point was higher than whatever the dew point was. And normally we would put some humidity control, which would look at the dew point and say, hey, we're going to turn off the heat pump, or when it's not, when we don't want the floor sweating, that kind of thing. So the valves in the Viessmann kit is the 120 volt valve. You're going to buy two parts. You're going to buy the mixing valve kit, which is the motor actuator and the strap-on temperature sensor. This is a 10K NTC thermistor, and that's what the heat pump is going to be looking for. And the valve body. And this valve body shows a welded valve, and that's necessarily a welded valve. That's why it says may not be exactly as shown. And this would be ordered as a separate part number. And the reason why we do that is this is standard for every mixing valve we're going to use, but the valve could be a 3/4 inch, could be a 1 inch, could be an 1.5 inches. We don't know what valve size you're going to want, so that's why you order the valve body different. This motor will fit on any of the valve sizes that we supply. Now, there's another option here. What if I have hot water, chilled water here, but only hot water here? I don't want to have any application where in the summertime, I'm going to send chilled water out to this radiant floor for the reasons I talked about earlier. Is you're not going to want a floor sweating with a 45-degree water temperature running through the floor heaters. So there are two ways to control an optional valve here. We're going to put this valve in here, and there are two ways to control it. It's going to be used on the VCH output valve control, but it's either powered open spring return, just like the other valve we looked at. But because this has two outputs on it, it could be powered open, powered closed type valve. So it's your choice how you use this. But the idea is that we're going to close this valve whenever it's in the chilled water mode. So when we look at the control here, we can say that in the heating mode, it will allow water to flow through here. So we're going to power the LH, and means we're going to have an open circuit here. So that's a little different than the other valve we looked at. So make sure we pipe the valve correctly. We're going to want water passing through here in heating mode. So when the unit is in heating mode, the VCH output will power LH. So that's why over here we're going to say in a two-way valve, we're going to power the valve open. In a three-way valve, we're going to bypass water this way and not let the water go this way. And I'm showing you in this drawing a two-way valve and a three-way valve and the two powered open spring return. It could be either way, but either one of these could be powered open, powered return, or powered open spring return. I just was trying to declutter the drawing a bit. And when is this valve triggered? Well, the valve is triggered whenever this control is set in heating mode. So heating, DHW, you see here are highlighted. That's the standard function for the heating mode. You turn this dial so that you have heating and domestic hot water initiated, and it will open this valve. It will open the valve this way, and that allows the hot water to go through the system and come back. Now, when the system is in cooling, okay, so we have the cooling and domestic hot water function. This valve is unpowered, the spring return valve, and this valve is powered on the cooling side, which blocks flow this way and allows still water to go this way. So if this pump is running, and like I said, you can use a two-way or three-way valve. I prefer the three-way valves because if I use a two-way valve and this pump is running at some point in the summertime, even somebody testing it or running it, or it's plugged into the wall and it's whatever the scenarios where this pump might run in the summertime, if I don't have a three-way valve, this pump is going to pump into a dead head, and that's going to be detrimental to the life of the pump. So now we look at an even more complicated or maybe more elaborate system. We still have the heating cooling valve here, but we have circuit one is broken into two groups. We have the air handler, which has its own pump. We have the panel rads, which are going to use the heat cool circuit pump. Now, this is going to be calling for heat and it's going to run the pump whenever this is in that mode. And this is going to run the pump for heating and cooling. And this logic is going to be whether the buffer tank is whether it's hot or cold. It's going to be based on that temperature sensor in the buffer tank, which is, remember, circuit 1, and the setting of the control, which is set for heating mode, right? The heating and domestic mode. And then we have the second circuit. So in this case here, we have circuit 1. It's going to run its own pump for the panel rads, and the air handler is going to run its own pump internally. Now, if we add now the heat circuit 2, so we have these two systems running at the same set point for circuit 1, and we have this system running at its different set point with a heating curve. The mixing valve can turn the higher water temperature we're going to obviously see for these two systems. Going to turn it down. And the pump then is going to be running through here, and this sensor that's heat cool circuit sensor 2. This is going to drive me nuts. We got to find a better way to talk about this, Pat.
Energy circuit. Or
yeah, I know.
Energy circuit.
Yeah, that's what you keep saying, and I keep forgetting. This valve here will then maintain the mixed temperature by bypassing some water here. So this is circuit 1 now and circuit 2, both enabled, but circuit 2 has 2 loops, one with the pump running from the indoor unit and one running with the pump from the air handler. And again, none of this has a thermostat or a dry contact or anything that comes back to the indoor unit. The indoor unit is maintaining the buffer tank, and these systems are drawing off of the buffer tank. So you don't have this thermostat or the call for heat from the air handler coming back here. You don't have a end switch on a zone valve coming back here. You just have these running as a building loop and pulling energy off the buffer tank, and the buffer tank's being maintained. Now, when I've done it this way, you can see that now it might be even more important to have this bypass valve in here, because we have 2 circuits. One's hot water, chilled water, and one's hot water on the same energy circuit. So again, this valve here becomes more important because we certainly do not want chilled water running to these radiators. Now we add domestic hot water to this. So now this looks like a more complete system. We have DHW, we have circuit 1, which has got 2 different loops. We have circuit 2, which is a mixed circuit, right? So this is a complete system now. And we can see that we add the domestic hot water, we add the domestic hot water sensor, and the control for the recirc pump, right? Now, when we look at this thing as a whole, this is a system drawing that shows everything. Now, we're going to look at a couple of things we didn't see or we didn't examine. The first is the room temperature sensor. This is optional. If you had a house that there was a common area in the house where the thermostat was maybe, and it was a good reference point for the building's temperature, and there wasn't a lot of controls on the radiator, so there wasn't zoning every room. If you had a zone in the room where the thermostat's in, obviously there's going to be a conflict there with this heat pump making heat when the thermostat is closing and opening valves. So this would be in a system where you already have a central thermostat, and you want to know the room temperature so the heat pump can maintain the buffer tank temperature based on room temperature. So the room temperature feedback then will help this buffer tank adapt to the room temperature, up or down based on water temperature, up or down based on the room set point. And we've also shown here the outdoor temperature sensor. So the outdoor temperature sensor would be hopefully put it on the north wall of the building, so it doesn't see the sun, northeast maybe, and it shouldn't be too close to the heat pump. And all of our drawings show they're pretty close, because this is going to be pulling heat or rejecting heat, and the outdoor temperature sensor is going to see maybe a blend of that temperature. So just like you wouldn't put the outdoor sensor near the exhaust on a boiler, you don't want to put it too close to the heat pump as well. And then we show again the connection between the boiler and the backup boiler and heat pump here. The indoor unit, and this one other line we haven't talked about at all. This other line here is the communication bus. So the outdoor unit gets all of its commands to set point and whether it needs to be in heating or cooling from the indoor unit. And the indoor unit's going to have all the control logic in there. So, and the really great thing about this is the indoor unit will give you all sorts of diagnostics on what the outdoor unit is doing. If you want to know the fan temperature, the fan speed, the refrigerant pressures, the refrigerant temperatures, All of that can be measured from the indoor unit controller. So troubleshooting makes it very easy. Before you get out there and try to figure out what's wrong with the outdoor unit, you can take a look at the indoor unit and do a diagnostic to see where you need to start with looking at that. So this is kind of just an overview of the entire system, showing the wiring to the communication, the outdoor sensor, the indoor sensor, and all of the things we talked about here in the seminar today. Now, if you want more information on this, there are two QR codes here which you can click on, one's for the US, one's for Canada. Basically, the Pro Toolbox is the same information, but this takes you to the US website, this takes you to the Canadian website. So if you want to dig somewhere else, find your sales rep or whatever, it's much easier if you're on the website you're on. So we have all of this information within the CA or the US Pro Toolbox. Any questions?
We do have some questions. Can you actually go back to slide 38, I think it is? Sure. Yeah, slide 38. Just back 3 slides overall. So one thing I wanted to point out is something that I've actually seen quite a bit is your circuit one with air handler and panel rads. I know at least where I'm at in New York, in upstate New York, we have a lot of areas where we have a basement air handler and an attic air handler. So just to think outside the box for everybody, that doesn't have to be panel rads. That could be 2 separate air handlers on that heat circuit one.
Yeah.
So I know I run into those systems quite a bit. It's easy ductwork, stuff like that for those retrofits. So keep that in mind. And then I want to leave it here because we had a great question actually earlier on, which came in anonymously, and that's quite all right. But will the indoor unit pump still circulate if the backup boiler is piped directly on the buffer tank and in an operating standpoint? So I did answer yes. If there's a call for heat or chilled water, regardless of what there's a call for, the indoor unit pump operates. I'm assuming it's because we were talking about DHW and piping that backup boiler that we're looking at here, not directly to the buffer tank. And there's a couple reasons actually why that is. One of the reasons, one is pipe sizing. Your system actually might only be piped off of that indoor unit, say in 1 inch, perhaps to your buffer tank. You know, it might be 1.25 inches. We should have 1.5 inch piping going from the indoor unit to the DHW tank for the flow rates that are necessary, all the things making domestic hot water at low temperatures. So although you could pipe your backup boiler to the buffer tank, and with all the pumps running, it theoretically would go back through the return and into the indoor unit and go to the DHW tank in all theory, that would work. It's just going to take a lot longer for that DHW tank to satisfy and potentially choking down the flow rate that you could achieve going to the DHW tank if they were completely separated. So it came in that point. So I don't know if anybody else had that thought, but
yeah, which is exactly why we show most of our drawings with the boiler in closely spaced tees between the indoor unit and the outdoor unit, because then it solves all those issues.
And we have, I've actually got 2 more in here. Will the recording be sent out? So if anybody didn't see that question, we don't send the recording out for every presentation to every attendee, but we will post this on our Viessmann North America YouTube channel, which is Viessmann Climate Solutions North America. So we will have these recordings posted there. The next question actually gets into a wiring question. So as Mark mentioned earlier, we did a wiring webinar a couple weeks back. Mark, you did one, and that, if it's not already up there, should be up there in due time.
I talked to Danielle about that this morning. She's going to try and post it this week.
Yep. So that should be up there as well. It does take some time to go through, edit out all the unnecessary stuff. So we usually cut those recordings down quite a bit so you don't have to listen to a lot of banter. But was the question is talking lastly about that Modbus and interconnect communication wire. That is just that. It's just a communication wire. And the question came in is, does the outdoor unit get its power from the indoor unit like we would see with a mini split? And no, these are a separate 240 volt, 208, 230 volt to the indoor unit and separately to the outdoor unit. So with the indoor unit having those electric resistance elements in there, there's going to be quite an amp draw when those are engaged. So that's a separate 40 or 50 amp double pole breaker, depending on the model size you have. And then the outdoor unit is again a separate 208, 230 volt double pole breaker that's going to be, 20 to 45 amps, if my memory serves, depending on the model size. So make sure you do follow all electrical codes and things like that.
And one other thing to point out is the indoor unit is a 4-wire, so it's line neutral ground. So you need a neutral. The outdoor unit doesn't need a neutral, so it's just line ground.
Correct. Those were the 3 questions we had open. Great questions, so I'm glad we got to use that. Another one, can I use the same tank for cooling and heating? I see the buffer tank inside the package and assume it's not sized based on the minimum BTU requirement for a zone. So the buffer tank that comes with the package is both a heating and cooling buffer tank. If you do already have one on site or you're setting up a system that would be potentially in, say, a cooling dominant market, and you were pairing it with DHW, there is a possibility that tank might not be large enough based on the flow rates and storage capacity you have in that tank to operate, say, an air handler for the 20, 30, 45-minute turnaround, depending on what size tank and size unit you have. There's a lot of variables in that. But if you are using a tank that is on the open market, make sure it is a cooling buffer tank and not just a heating buffer tank. There's going to be a lot more insulation on the cooling buffer tank. Same thing with domestic hot water tanks. If you're going to choose somebody else's tank or it's already pre-existing, make sure it's good for low temperature applications. We're only supplying 140 degrees out of the refrigerant circuit alone. With that backup element heat, after a time delay, you can boost it up to about 160, 165.
Yeah, but only below that heat enable point, the electric heat enable point.
Correct. Yeah, middle of summer, you might not have. You really shouldn't need the electric elements to come out in the middle of summer. You're going to make DHW real fast when it's hot out. So
when it's hot outside, yeah.
Yeah.
Yeah, the buffer tank size is, like I said, it's 75 liters or just about 20 gallons. So you have to kind of look at your system design and say my air handler is going to use so many GPM and kind of decide your tank is going to take so much time to recover, decide whether that buffer tank is large enough for that application. Yep. We'll see you later, guys. Thanks for coming.